Okay, to find the inverse of 2x minus 3, we'll go through the four-step algebraic process. First, we'll change the f of x to y, just because it's easier to write y than it is to write f of x. That's the first step. The second step is to switch x and y. Wherever we see a y, we put an x. Wherever we see an x, we put a y. That's to effectively turn the output to the input and the input to the output, which is what the inverse does. It takes the output and sends it back to the input. Now we're going to solve for y. That's the third step. So we'll add 3 to both sides. And we'll divide both sides by 2. And then we'll call that f inverse. So f, that's the fourth step, is change it back to function notation. Call it f inverse. F inverse of x is x plus 3 over 2. Or if you prefer slope-intercept form, that would be 1/2 x plus 3/2. It's just the same function written in slope-intercept form. So that's your inverse function. F inverse of f of 2, if you just think about it, if you take 2 into f, that's f of 2. And then if you take f inverse of f of 2, you ought to get back to 2. That's, again, the whole point of an inverse. It takes you back to where you started. Let's see if that works. So we'll start with f of 2. F of 2 means I plug 2 into here. That gives me 4 minus 1, which is 1. And now I plug 1 into the function I just found, f inverse, over here. That gives me 1 plus 3 over 2, which is 2, just as we said it had to be. F inverse of f of 2 is 2, because f inverse of f of any number is that number. And in fact, f of f inverse of any number is that number. That's part of the definition of inverses. Check the handout that I posted under downloads. All right, sketch these guys on the same graph. The easiest thing to do when you have a line is find the intercepts. So obviously minus 3 is the y-intercept. So if I set x equals 0, y is minus 3. So minus 3 is the y-intercept. With a little bit of calculating or solving, you can find the y-intercept. Just set x-intercept, sorry, set y equal to 0 in the original function, and then solve for x. You get x equals 3/2. So 3/2 0 is the x-intercept for f. And f inverse, then, it just switched. If f takes 0 to minus 3, f inverse is going to take minus 3 to 0. So that's going to be the x-intercept for f inverse. And if f takes 3/2 to 0, f inverse will take 0 to 3/2. That'll be the y-intercept for f inverse. So they just change roles. So for f, you have a y-intercept of minus 3 here. And you have an x-intercept of 1.5, 3/2 there. And so you draw a line through those 2 points, and you get something roughly like that. That's f. And then for f inverse, you just switch them. So the y-intercept was minus 3. So for f inverse, the x-intercept is minus 3 right there. And for f, the x-intercept was 1.5 or 3/2. So for f inverse, the y-intercept is 1.5. And now we can draw the inverse roughly like that. And then this should be symmetric with respect to the line y equals x up to the quality of my drawing here. And this is y equals x, which should be the line of symmetry between them. All right. So when you have a line, when you're asked to graph a line and its inverse, the easiest way to do that is just to find the intercepts for one of them and then switch them to get the other one. All right, x squared, we know what that looks like. Start with minus 2, goes to 4. You square minus 2, you get 4. You square minus 1, you get 1. You square 0, you get 0. 1 goes to 1, 2 goes to 4. So to graph x squared, this looks like that. 1 and minus 1 go to 1. 2 and minus 2 go to 4. And you can keep going. 3 and minus 3 go to 9. The familiar parabola from algebra 1, x squared looks like that. All right, the domain and range for this guy, the domain is all real numbers. There are no square roots of negative numbers or division by zero to worry about. So any real number will do. And the range is y greater than or equal to 0. Because all of my outputs are 0 or more. So I can't get an output that's less than 0 from squaring. I'm always going to get a positive number. And I can get as low as 0 when I give it 0, but I can't get any lower. All right, it doesn't have an inverse because it fails the horizontal line test. Draw a horizontal line, I can go through these 2 points. The problem is when I take 2, I go to 4, and I take minus 2, I go to 4. So it's okay going out. 2 is uniquely 4, and minus 2 is uniquely 4. But coming back, I don't know what f inverse of 4 is supposed to be. Do I make it 2, or do I make it negative 2? And I can't use both because every input has to have a unique output. So that's the problem of not being a one-to-one function. You're function going out, but coming back, you're no longer a function. So for this, you can say fails the horizontal line test, or you can say that f of 2 equals 4 and f of minus 2 equals 4. That's the problem. And you could pick another pair, 1 and minus 1, or a half and minus a half. All those symmetric pairs of inputs will have the same output. So to get a function that has an inverse, I have to get rid of half of it. So what I have to do is create a new function that's just half the old one. So I'm just going to go like this here, just this guy on this side, just the right half. So if you say y is greater than or equal to, x is greater than or equal to 0, now I have an inverse because that function is 1-to-1. So in other words, if I just draw that now has an inverse. All my horizontal lines go through that thing one time. So that is a one-to-one function. So it does have an inverse, and the inverse is the familiar square root that we're used to. So f inverse of x would be the square root of x, where the input has to be positive. And it's unique because when we take the square root of 4, for example, we take the square root of 4 is just 2, not plus or minus 2. It's only the positive root because we got rid of the left-hand branch of the parabola when we defined the function f before we took the inverse function to be the square root. And to sketch the inverse over this, you just, first of all, we only care about the positive inputs now because we've gotten rid of these guys. So this stuff is no longer relevant. And now we go backwards to get the inverse. We just plot all our points in reverse. So 4 goes to 2 because the square root of 4 is 2. And 1 goes to 1, which is here, and 0 goes to 0. It kind of looks the same, but probably a better picture here. Looks like this. Let's draw both functions more carefully. So f, you have 0 goes to 0, 1 goes to 1, 2 goes to 4, and 3 goes to 9. looks like that. And the inverse function, just reverse all those. So 9 goes to 3 because the square root of 9 is 3. 4 goes to 2 because the square root of 4 is 2. 1 goes to 1 and 0 goes to 0. So it looks like that. Oh, the domain and range of f inverse. So this is f inverse in blue here. So the domain for that function is, I should put it in blue then. The domain is x greater than or equal to 0. The square root function is defined for positive x and 0. You can take the square root of 0, non-negative I should say. And the range is also greater than or equal to 0. The output for the blue function is everything above 0. So any possible output, any output that's positive is possible if you take a large enough input. You can even get a number whose square root is 1,000,000 if you make x big enough. Make x 1,000,000 squared, and then the square root of x would be 1,000,000.